Hello, our lesson for today is about the serial in, serial out register or SISO. Here is our simulation design circuit for implementing the serial in to serial out transfer of binary data. The circuit is composed of 4 D flip-flops with preset and clear inputs that are activated by logic 0. Serial data bits are loaded at the D input of the first flip-flop. At the arrival of the clock signal, the first data bit is loaded to the Q output of the first flip-flop, flip-flop 1. The next data bit is loaded to the first flip-flop only upon the arrival of the second trigger pulse from the clock source. The next flip-flop 2 gets its input from the output of the first flip-flop, so that whatever output of flip-flop 1 will be transferred to flip-flop 2 at the next clock signal. The same condition will happen to flip-flop 3 and flip-flop 4, since the output of the previous flip-flop becomes the input of the next one. Notice that the D input of each flip-flop is connected to the Q output of the previous flip-flop except the first flip-flop, where its D input is connected to the data source via SW1. During the arrival of the succeeding clock signals, data is shifted to the right one at a time. That means the output of the next flip-flop will be the output of the previous one. The outputs of 4 flip-flops are being monitored by the 4 LEDs D1, D2, D3, and D4. At this point, let us now simulate this operation. First, let us initialize the outputs by making sure all flip-flops are cleared. This can be done by switching SW3 to ground or down position and then switching it back to up position. Notice no LED is lighted at this time to indicate all 4 flip-flops are cleared. Let us assume that our 4-bit serial data is 0101 and is inputted from right to left, 1 being the first data bit. Let us set SW1 to up position. To load the data to our first D flip-flop, we will now press SW2 once. You will notice that LED D1 is lighted, but D2, D3, and D4 are not. For the next input, let us position the switch SW1 to down position to correspond to a 0 value. Let us press the clock switch SW2 to load this value to the first flip-flop. Notice that D1 now is off and D2 is on. D2 is lighted because its input is previously the output from flip-flop 1, which is 1. For the next data input of 1, we set SW1 to up position, then press and release SW2 once. If you will notice, all the output states of the flip-flops are shifted to the right one at a time as SW2 is activated. For the last input of 0, place SW1 to down position and apply clock signal by pressing SW2. Notice the conditions of the 4 LEDs. If we continue to apply clock signals with SW1 in the down position, there will come a time where all output levels of 4 flip-flop become 0. By permanently positioning the switch SW1 to up position and continuously triggering the clock inputs, you will notice that after 4 clock transitions from 0 to 1, all 4 flip-flops will have high logic levels. In summary, serial in, serial out register operates by transferring data from the data source, which is inputted to the D input of the first flip-flop one at a time, and then retrieving this serial data at the serial output terminal, which is the Q output of the last flip-flop 4. That ends my presentation. Thank you very much.